Hello, everybody. Welcome back. We are just one video away from being able to define and talk about Markov chains. In the last two videos, we reviewed some concepts from probability, mostly focusing on conditional probability. And those probabilities were about events that we called capital A, capital B, capital C, and these were outcomes of experiments involving randomness or probability. So we rolled a fair six-sided die and maybe let A be the event that we saw an even number. In this video, we are going to rehash what we did in the last two videos, except we're going to pull it into the context of random variables. Random variables can be either discrete or continuous, and if that doesn't make sense to you, then you might want to go check out videos 1 through 7 in my basic probability series. But if you're ready to go, we are only going to talk in this video about discrete random variables. So remember, a Markov chain is a stochastic process with a property that we've yet to define. And a stochastic process is a sequence of random variables, an x1, an x2, an x3, possibly an x0, and those random variables can be either discrete or continuous. In this video, we're only going to talk about the discrete case, and I'm actually going to hold off on the continuous case until later in this video series so that we don't waste all of our beginning excitement. I'm going to learn Markov chains, energy on review. So we want to start with a discrete random variable Markov chain, so I'm only going to review the discrete random variable stuff right now. It's convention in probability and statistics to always use capital letters to denote random variables, like capital X and capital Y. And for a discrete random variable, it's allowed to take on values in a discrete space. So it doesn't have to be finite. It might be all integers, -5, -4, +7, all integers. It may be all positive integers. It may not be integer valued at all. So our random variable X could take on the values maybe 1 and then 1.1 and 1.2 and 1.3. And if we continue in that way, we're looking at discrete values on a number line. We are at no point allowing the random variable X to take on values in a continuum. So they can be separated on a number line, and therefore it's a discrete random variable. But we want to talk about the probability that our random variable X is equal to, say, 3 or 1.7. And we want to be able to talk about that a little more generally with a formula that we can plug 3 into or plug 1.7 into. So the probability that capital X equals little x is going to represent the probability that the random variable X equals whatever we're going to plug in for little x. So the little x is a placeholder. And for a random variable Y, the probability that the random variable capital Y is equal to little y, we can write that like this. And finally, we can put them together and write the probability that X equals X, comma, Y equals Y. And that comma can be read as and. It's just like an intersection if these were events. And so putting these probabilities together in one statement like this is known as a joint probability. So if you have a joint probability, you can talk about something known as a marginal probability. For discrete random variables, the joint probability that X equals little x and Y equals little y, we might be able to write that down in terms of a formula involving little x and little y that we can plug things into. But often in the discrete case, joint probabilities are given in a tabular form like this. So in this little example here, I have a random variable X. They can take on the values 1, 2, or 3. And a random variable Y that can take on the values 0 and 1. And inside the table, I have a bunch of probabilities. And so if you want to find the probability that the random variable X equals 2 and the random variable Y equals 0, you just have to look in this table right here. So that's 0.05. Now suppose I wanted to know the probability that X equals 2, and this really has nothing to do with Y. So if you look at all the outcomes here, there are 2 places where X equals 2. And you can think of these as disjoint events. So one of them corresponds to the event where X equals 2 and Y equals 0. And the other one corresponds to the event where X equals 2 and Y equals 1. And those two things, each with two things, can't happen at the same time. And so we've got disjoint event probabilities, and to get the probability that either one of those happen, we can add them up, and we do, and we get 0.15 for the probability that x equals 2. So you can see that when we started with joint probabilities for x and y, we can get down to a probability for x alone by summing things, and then we find those probabilities in the margin. For that reason, if you have a joint probability and you sum one of the random variables out to get down to a probability for a single random variable, that is known as a marginal probability. And it's also true if you have a big fat joint probability with lots of random variables like x1, x2, maybe out through x10. If you sum some of the variables out of that and maybe 7 of them out, and you leave yourself with the joint probability for x1, x7, and x9, that's still known as a marginal probability in the context of coming from the probability with way more random variables. Let's write this out a little more generally. If you have a joint probability that x equals little x and y equals y, then you can get the marginal probability that x equals x by taking the joint PDF and summing over the values of little y. Similarly, you can get the marginal probability that y equals y by taking the joint probability and summing over all the values for x. And these functions over here of x and y are known as probability mass functions for the random variables x and y, respectively. Now, in the previous 2 videos, we talked a lot about events, outcomes of experiments, and we called them capital A, capital B, capital C, and these were not random variables. These were descriptions of things that are happening in an experiment. So if you have a random variable x, we can talk about it equaling 3 or equaling 1.7 or in general equaling a little x. And we can refer to that as an event. I'm going to let A be the event that I observe the random variable x to equal some little x. I'm going to let B be the event that I observe the random variable y to be equal to some particular value, little y. And so we had a conditional probability definition for A given B. The probability that A happens, given that you know B happens, is equal to the probability of the intersection of A and B divided by the probability for B alone, which you've heard me say marginal probability in my previous videos, and now we have a formal definition for marginal probability. But my point is that if you let x equals x be one event and y equals y be the other event, then we can use this definition of conditional probability for events and translate it to the random variables. So we can talk about the probability that capital X equals some little x given capital Y equals some little y, and this would equal the probability of the intersection, so the event where x equals little x, comma, and y equals little y, divided by the probability that y equals little y. So one of my favorite things that we've already talked about is unraveling the definition of conditional probability. So in this case, you maybe don't have conditional probabilities in your mind or in the orbit of the problem you're working on. You really want to find the probability of an intersection of 2 events, but it may be convenient to look at conditional probabilities, in which case we can take our definition of conditional probability as the probability of an intersection over a marginal probability and move things around so that we can write the probability of the intersection as a conditional probability times a marginal probability. We did that for events A and B, and we can certainly do that for random variables and a joint probability like x equals little x and y equals little y. We have just talked about how the marginal probability that x equals x can be written as the sum over all little y of the joint probability that x equals little x and y equals little y. And now we have talked about how this intersection probability can be written in both of these ways. So let's say I write it as the probability that x equals x given that y equals y times the probability that y equals y. So if you go from this left side all the way to the right side, we just went through it to figure out how it goes, but eventually you're going to do this so much that you're going to go directly from here to here. And this is computing a probability for x by conditioning on y. Just like we saw in the event space, I only care about a probability for x, but it was helpful for some reason in the context of the problem to drag the other random variable in. So we can compute a probability for one of the random variables by conditioning on the other one. The probability that x equals x, if you sum that over all possible x, and by the way, if the random variable x only takes on the values 1, 2, and 3, like in that table, you can actually sum over every possible value of x you can think of, because if you hit in this sum, little x equals 1.7, the probability will be 0, so it won't add anything to the sum. So if you sum over all the possible x's and maybe throw in some extras, the probability is going to sum to 1. The conditional probability that x equals x given y equals y is still just a probability, but it lives in the universe where y equals y. It lives in conditional land. So if you were to sum the probability that x equals x given y equals y over all of the little x's, then that should be 1. You are in conditional land where y equals y, and really now, in that shrunken universe, you're working with the probability that x equals x, and you can use all of the rules of probability that you already know. So let's prove it. Okay, I'm going to take my probability that x equals x and y equals y and sum over all the x. We want to see if this is 1. I'm going to use the definition of this conditional probability. So I'm going to sum over x, the probability that x equals x and y equals y divided by the probability that y equals y. Now this denominator can be pulled outside of the sum. And so really I'm left with the sum that x equals x and y equals y. And that will give me the marginal probability that y equals y. And because I have this 1 over the probability that y equals y out front, we get cancellation, and we do see that we get 1. Remember Bayes' rule? This was for reversing the direction of conditional probabilities in the case that they seemed backwards and unnatural for you to compute when we were talking about drawing balls out of boxes. Now, you may have someone giving you, or you have some problem where you know the probability that x equals x given y equals y, and you want to turn it around, and that probability you don't know and may be difficult. So Bayes' rule is going to apply here as well. Again, we're thinking of the event that x equals x as, well, an event. Call it A, and let B be the event that y equals y, and our previous rules apply. So suppose I know the probability that x equals x given y equals y, but I want to know the probability that y equals y given x equals x. By definition, this is the probability of the intersection over the probability that x equals x. I'm going to unravel the definition of conditional probability to rewrite the intersection as a conditional probability times a marginal probability. And there are 2 ways to do this, and one of those ways is just going to get us back to the unknown we started with, so we don't want to use that one. So in this case, I'm going to write this intersection probability as the probability that x equals x given y equals y times the probability that y equals y. If you know the probability that x equals x, then you're good to go. But if not, you can find the probability that x equals x by conditioning on y. And that's how we get this denominator here. So overall, from this left-hand side to this, we have what is known as Bayes' rule. We have started with a conditional probability in a direction that was not useful to us, and we turned it around. Now, if you've already had probability and are up on your probability, none of this stuff would be new. But I'm thinking possibly what I'm about to talk about might be new for you, and that is called double conditioning. We talked about finding the probability that x equals x by conditioning on another random variable y. But what if the goal is to find a conditional probability, the probability that x equals x given y equals y? And what if that was difficult to compute, but for some reason it would be easier if we brought in another random variable z? So what we're going to do now is find the conditional probability that x equals x given y equals y. So it's already conditional. We're going to find that by conditioning on z. So I'm calling this double conditioning. Before we do that, note that we don't ever write the probability that x equals x given y equals y given z equals z. We're going to bring that information in. We're going to be given that z equals z. There's just no reason to write two conditional lines. It's like someone gave you some information on Monday and then they gave you some information on Tuesday. And so at the end of Tuesday, you are given a bunch of information. It doesn't really matter what order it came in. So we're always going to write the probability that x equals x given that y equals y and z equals z. So remember, the marginal probability that x equals x can be written by conditioning on y as this sum of this conditional probability times this marginal probability. And I claim, and we're going to prove this, but I'm just writing it now so you can see the analogy, the conditional probability that x equals x given y equals y, we can condition on a new random variable z, and we can write it as the probability that x equals x given y equals y and z equals little z times the probability that z equals little z given y equals y, and sum over all of the z's. So this might seem a little confusing, but remember what we said about conditional probability just being probability in another universe, in conditional land, in the universe where y equals y. So if I use, and this is just for this example, this is not something we're going to use, but if I write the probability that x equals x and condition on y equals y, if I write that as just the probability that x equals x, using another probability symbol that I'm going to call p sub y. Now I can use the rule above on this line, and all of these probabilities are in this conditional universe where y equals y. So now I can put that information back in, rewrite the subscript y equals y as a condition that y equals y, and that's how we get the second line. But let's prove that this actually works. The probability that x equals x given y equals y, I can write it out by its definition as the joint probability over the marginal probability. And I'm going to bring a new random variable z into the numerator. So I'm going to let z equals z as well, but sum out over all the z's so that this three-way probability when summed over z is actually equal to this two-way probability. I am now going to unravel my definition of conditional probability. There's many ways to do this. Before, we let A be the event that x equals x and B be the event that y equals y. Here, there could be an event C, but we could have A be the event that x equals x and B be the event that y equals y and z equals z. And then we can write the probability of A intersect B as the probability of A given B times the probability of B. So that's what I'm doing right here. If I let A be the event that x equals x and B be the rest of it, I have just unraveled the definition of conditional probability to write this intersection as a conditional times a marginal. Now I'm going to do two things at once in this next line. I'm going to pull out the 1 over the probability that y equals y, pull that out in front of the sum so that I get the sum of everything on one line. And I'm going to write the probability that y equals y and x equals x. I'm going to unravel the definition of conditional probability again. And I'm going to write that intersecting probability as the conditional probability that z equals z given y equals y times the probability that y equals y. Now, if I take this probability that y equals y, you can see it will cancel with this 1 over the probability that y equals y. And we're left with the sum over z of the probability that x equals x given y equals y and z equals z times the probability that z equals z given y equals y. And that's what we were out to show. As mentioned in an earlier video, there are so many ways to write out probabilities. For example, if you have events or sets A and B, and you want an expression for the probability of A union B, you could take, so that's going to be represented by this shaded area. You can take all of the area or probability for A and add it to all the area or probability for B, but you've double counted the center, so you need to take that out. But you can also write the probability of A union B as, this area represented as everything that's in A and outside of B, and the disjoint region, everything that's in A and B both, and the disjoint region, everything that's in B and outside of A. And I can think of many more ways. So here's just one more. The probability of A union B, which is represented by the total area here, can be written as the probability that B occurs plus the probability of the rest of this set, which is A outside of B. So this part of this set is A intersected with the complement of B. So you can see I've written out the same probability in 3 different ways, and I can think of several more. The same thing is going to be true for random variables. And if you try to memorize formulas, you are really not going to be able to do a problem with a slight tweak in it. So you really need to understand what's going on and rewrite all of your probabilities in terms of pieces you know. So again, in this slide, we have maybe a problem given to us where we know the probability of A intersected with the B complement. And we know the probability of B. So in that case, I'd want to use this expression. Let's look at it for random variables. The probability that X equals X and Y equals Y can be written as the conditional probability that X equals X given Y equals Y times the probability that Y equals Y. I'm not going to write it here, but it can also be written as the probability that Y equals Y given X equals X times the probability that X equals X. Let's look at the 3-way probability that X, Y, and Z are equal to little x, y, and z. Now I can write this as the probability that X equals little x given that Y equals little y and Z equals little z times the probability that Y equals little y and Z equals little z. This is just the probability of A intersect B written as the probability of A given B times the probability of B, where A is the event that X equals X and B is the event that both Y equals Y and Z equals Z. But another way I can write out this 3-way probability is as the joint probability that X equals X and Y equals Y in the conditional universe where I've been given that Z equals Z times the probability that Z equals Z. So again, this is us writing the probability of A intersect B as the probability of A given B times the probability of B, but now the event A consists of X being little x and Y being little y. Together, that makes up my event A, and the random variable Z being little z is the event B. So again, the probability of A intersect B is the probability of A given B times the probability of B. And so as long as you kind of define what pieces of the 3-way probability you want to be in A versus B, then you can write this down in terms of several different conditional probabilities. Let's look at yet another way to write out this 3-way probability. I can write it as the probability that Y equals Y given X equals X and Z equals Z times the probability that X equals X and Z equals Z. So this is just saying that it doesn't matter that the X is listed next to the Y. I'm going to let A be the event that Y equals Y and B be the event that jointly X equals X and Z equals Z. And we're doing the same thing here that we did before. And we can take it further if we want to, if we need to, based on the information we're given in a problem. Maybe I don't know this joint probability that X equals X and Z equals Z. So we can further break this down as the probability that X equals X given Z equals Z times the probability that Z equals Z. And we could break it down in the other direction. So what do? You break it down based on the information you have that you're going to use to solve the problem. So next up, we are going to finally be able to define and talk about Markov chains, the whole reason you came here to this video series. So I hope to see you in the next one.